All right, today we're doing something a little different. We're going to take a single, tricky problem from a university linear algebra exam and just tear it apart. We're looking at question number 7, a two-parter that, well, let's just say it's got a few surprises up its sleeve. Okay, so here it is, question 7 in all its glory. Now, on the surface, it looks like two pretty straightforward proofs, right? But here's the thing. We're not just here to find the right answer. Think of this more like a case study, some real mathematical detective work where we're going to question absolutely everything. So here's the game plan. First, we'll break down the challenge. Then we'll hit the eigenvalue proof, followed by that orthogonality test. And to wrap it up, we'll connect all the dots and see what we can learn from this whole thing. All right, first up, the challenge. So you can see that question 7 is really two problems masquerading as one. You've got part A, which is all about algebra, a specific matrix with some rules, and then part B, which is more about geometry, a general claim about vectors. The real question is, do these claims actually hold up? Okay, let's jump into the first part, proving the eigenvalue. The mission, should we choose to accept it, is to prove that -1 is an eigenvalue of this matrix. But there's a catch. It only works if the matrix's elements follow this one very specific rule. Before we go any further, let's just do a super quick refresher on what an eigenvalue even is. So an eigenvalue, which we call lambda, is basically a special number for a matrix. It tells you exactly how that matrix stretches or shrinks a certain vector, the eigenvector. The really cool part is that the vector's direction stays exactly the same. It just gets scaled up or down. That's what this classic equation, AV equals lambda V, is all about. So the big question is, how are we going to prove this? I mean, we could try to hunt down an eigenvector, but honestly, there's a way better, more direct way to do this. It involves connecting eigenvalues to another huge concept in linear algebra, the determinant. And here's the key, the big aha moment. A number lambda is an eigenvalue only if the matrix A minus lambda I is singular. And what does singular mean? It means it doesn't have an inverse and its determinant is 0. So for our problem, where lambda is -1, our entire complicated proof boils down to one simple goal. Prove that the determinant of A plus I is 0. That's it. Okay, so let's actually do it. Making the matrix A plus I is super easy, right? We're just adding 1 to the diagonal elements. But wait, look closely at what we end up with. See that second column? It's almost all zeros. And that, my friends, is a massive shortcut when we need to calculate the determinant. Yeah, because of those zeros, we can be clever and use cofactor expansion right down that second column. It makes things so much simpler. We're just left with one single term, b plus 1 times the determinant of that little 2x2 matrix. And once you crunch those numbers, you get our final expression for the determinant, b plus 1 times 2a plus 2 minus c. Okay, this is it. The moment of truth. The whole problem is built on the claim that this condition, a minus b plus c equals -1, is somehow going to force our determinant expression to equal 0. But just look at them. It's not exactly obvious how one leads to the other, is it? So you know what we do when we're in doubt. We test it. And this is where the whole thing just falls apart. It's actually pretty brilliant. Let's just pick some simple numbers that fit the rule. How about a is 1 and c is 1? Okay, if we do that, the condition forces b to be 3. Simple enough. Now let's plug those numbers into the determinant formula we found. We get 3 plus 1 times 2 times 1 plus 2 minus 1. That's 4 times 3, which is 12. And last time I checked, 12 is not 0. So what does this mean? It means the question is just wrong. The whole premise is flawed. That condition they gave us, it does not guarantee that the determinant is 0. And honestly, that's such a cool lesson, right? Sometimes the most important thing you can do in math is to prove that something is false. Okay, so part A, the algebra part, completely crumbled when we looked at it closely. So now let's check out the geometric side of the question. Maybe its logic will be a little more solid. Let's see. All right, here's the claim for part B. It says if you have two non-zero vectors, u and w, and they're both orthogonal to some other vector v, then u and w have to be linearly independent. And you know what? That sounds pretty reasonable. You can kind of picture it, right? It feels like they have to be pointing in different directions. But as we all know, feeling isn't a proof in math. So we have to ask ourselves the most important question in math. Is this always true? Does it hold up in every single possible case? because all it takes is one counterexample to bring the whole thing crashing down. So what if U and W have some kind of relationship with each other? And bam, here's the counterexample that just blows it up. It's actually really simple. Just picture this. Let vector v point straight up along the y-axis, and let vector u point straight out along the x-axis. They're orthogonal, right? Perpendicular. Easy. But now, what if vector w is just double the length of u, pointing in the exact same direction? Well, w is also orthogonal to v. But are u and w linearly independent? No way. W is just a multiple of u. They're linearly dependent. The problem, the hidden flaw, is something called collinearity. The question setup doesn't say anything to stop u and w from being on the exact same line. And as long as that line happens to be perpendicular to v, well, the conditions are met, but the conclusion, linear independence, totally fails. So this brings us to what actually does work. If you want to guarantee that a set of vectors is linearly independent, what you really need is mutual orthogonality. That means every vector has to be orthogonal to every other vector. So u is orthogonal to v, w is orthogonal to v, and, this is the key, u has to be orthogonal to w. The original question was just missing that last absolutely crucial piece of the puzzle. Wow. So both parts of question 7 turned out to be wrong. They were built on flawed claims. So what have we learned from all this, besides just the nitty-gritty math? I mean, this one question was basically a masterclass in how to think like a mathematician. We saw firsthand why you always have to test claims with counterexamples. We learned that you have to know the exact conditions for big ideas like eigenvalues and linear independence. But honestly, the biggest takeaway from me is this: trust your work. Trust your process, because sometimes the most powerful thing you can discover is that the question itself was the problem all along. And that leaves us with a final thought to chew on. You know, linear algebra is this beautiful bridge that connects the world of algebra with the world of geometry. But what we saw today is that if the algebraic rules on one side of that bridge are flawed, the geometric picture on the other side just completely falls apart. It's an amazing reminder that in math, every single detail, every condition, every little symbol, it all matters. Thanks so much for digging into this with me.